Okay, cześć wszystkim. Cześć wszystkim. Are we doing English or Polish? What are you guys? Say it again? Okay, let's do English because I do this in English, so that's easier. Basically today I'm going to talk about how to deploy a language model on AWS Lambda because they became so small and small practical at this point, and Lambda became so big and so practical at these sizes as well that we can actually do this. And you know, of course, on Lambda we don't have a GPU. We have limited resources, but this still can be useful. And this is something I did for few use cases, and that's what some other people are doing as well in some pretty interesting places, I think. But in general, this is a ridiculous idea because Lambda is a runtime that's designed for short and small pieces of work that you do at will. You have, you know, this great scaling, and in general, the code and the body of the function is supposed to be small. Whereas where you take an LLM at a usable size, you're looking at few gigabytes. So how can we do this? And is this really practical? So in this talk, I'm going to show you basically how to do this, what you can learn from this, and what are the cost calculations and performance calculations, because I run it on few samples so you can see what's happening as well. Yeah. Basically, what we're going to end up with is just an API that you can call with a prompt and get a reasonable answer. It's going to be based off one of the more performant small LLMs, small large language models, small language models. And in this case, you know, when I was deploying this, I was actually recruiting senior engineers. So I thought, okay, let's ask what are the good questions for an interview here. So when it comes to me, hello, my name is Karol. And what I do right now is I'm a staff software engineer at a fintech company. But before I was also a head of engineering of a 25 people engineering department at a startup. So now I'm on the other swing of my engineer manager pendulum. And what I do is I develop some products myself as well. And I worked on several AI products and introducing AI functions to existing products as well. Because what you can see, and I just got entangled in my mic. Give me a bit. Because what you can see in products these days is you either develop a full AI product or you develop an AI function for your product. So this can be used for, say, this one of these AI functions. So the current situation is, you know, LLMs are great. We've checked out some use cases and we found that users are paying for some of them, or at least are happy with some of them. But the problem is that they are available through managed APIs, and in 99% of cases you should use those managed APIs because they are, I think right now, even subsidized by VC, because those APIs have no business being this cheap in many use cases. But if you want to have something use case specific, if you want privacy, if you want control, you can use this approach. And there are several use cases for self-hosting. In this case, we're going to use running LLM at a CPU, so at Lambda. So if you have something small enough, you can run it this way. Also, in this exercise, we're going to pretty much take a Docker image and host it on AWS Lambda. And this is one of the features that not many people are aware that exists. So you don't need to use the runtime that AWS provides for Python, Node, or whatever. You can basically ask Lambda runtime to run your own Docker container as long as it exposes some of the methods that the Lambda runtime can use. And actually, the most successful thing I did with running Docker image in AWS Lambda was when I was working at a cybersecurity company, and we were basically ingesting 1 trillion log lines a year, so 100 billion a month. And we needed rapid scalability at peaks because basically we're analyzing bot traffic and blocking bots when they were attacking websites. So we needed a real-time ingestion of data so we can pass it through our machine learning models. So we had a regular Lambda with Python, but it turned out it was slow and expensive. So we tried to, all of the optimization techniques to make the code smaller, to make the cold starts shorter, to make it more performant, but we ended up with basically developing the smallest image Docker image we could, and this was running faster than Lambda just loading Python code on our end because we had only the dependencies we've needed. So that's a good use case that maybe can be your takeaway from it. So how to deploy Lambda with a Docker container. But other cases, fine-tuning your own models, that doesn't have to be an LLM, but if your use case is few gigabyte large model and 6 cores of CPU and 10 gigs of RAM are enough for you, then you can do it via Lambda. And what is really interesting, several companies are now toying with going very granular with sandboxing of their users. So if you worked at enterprise software or you prepared a SaaS for someone, there often is a case where you need to deploy a separate piece of your system for a customer, for a large enough customer, or maybe you deploy instances of your API per customer because of privacy, because of SLAs, because of regulatory requirements. So in this case, and in some cases, some companies even go as low as, say, SQLite database per user. So with this use case, if you don't have a one homogeneous AI model that you use for everyone, but say you have an AI model per user, running it once a day, Lambda may be a runtime you can use because it will be just instantiated whenever you need it, and that's very rarely. In other cases, when you need just to host something, as I will show you, the cost parity with managed APIs is not there, but it's not that far off. Of course, full control over privacy, data security, you're not sending stuff to OpenAI, cost is questionable, and yeah, we can learn from this, as I've mentioned. So alternatives, how can you deploy LLMs in general right now? So there is SageMaker inference on AWS, but that's interestingly also CPU and up to 6 gigabytes of RAM, the regular model running without like GPU clusters, so that's similar to Lambda. You can create a cluster, Kubernetes or ECS. There's Google Cloud Run, where you can just run containers as well, like in Lambda. It's better branded and it's pretty clear from the documentation that you can do this, but it's also only CPU. When I was researching this, if you're into LLMs and models, you probably know Huggingface. If you don't, Huggingface is like a GitHub for AI models. You can find data sets, training recipes, and also just models ready to use there. So if you need a model to run locally, you go to Huggingface. If you want to learn something about current AI, probably go to Huggingface community. There's all sorts of tutorials and documentation. So if you just want to dive deeper into this, Huggingface is a good place. And actually, they offer a way to run small models at will whenever you want through their GUI pretty much. And the specs are pretty similar to what we're doing here. CPU up to 10 gigabytes of RAM. That's exactly that tops Lambda capabilities. So they are just using Lambda for small models. You can also deploy very easily bigger models there, but this requires spinning up an instance, and you pay for running an instance, but it's easier. And then we have Lambdas, right? So up to 10 gigabytes, max 15 minutes runtime, max 6 cores. It became beefy in the recent years. Like that's quite a lot, actually. Should you do it? We'll see. So the plan is, let's start with creating a small Lambda function with Docker locally. We're going to add an LLM to it. Then we're going to deploy it to AWS, and I'm going to show you some performance tests. So with this one, I didn't create a Terraform or CDK script, but but some bash commands just to make it, as easy as possible. But we're going to go through the process so we can do it in a script that's probably easier. But I wanted to, come back to the basics like we did years ago. Let's try bash script. And then if you are in general just want to see the code and stuff, it's there on my blog. And if you go to LLMs in the menu, there is the first article. There is this one, contains all the code. So for the environment setup, we're not going to through this, but you need AWS account and AWS CLI. What we're going to do today is in a free tier, so no worries. Docker installed and some IDE. I used Visual Studio Code. So a basic Lambda function in Docker is as basic as you can do it in any other way. So basically, we're creating lambda function.py. If you're going to add some dependencies, add them in your favorite way, requirements, UV, poetry, whatever. And then we're going to create Docker file and Docker compose YAML just for local testing. So this is our Lambda code. We're just getting data from Lambda, which is event and context, and I'm going to just print out a string at first. And this is going to be our first bare bones Docker file for Lambda function. It's as easy as this is. So the easiest way to do this is start with a provided by AWS container base image, because that gives you everything, and you just point it on your Python script or whatever language script. So that's pretty much similar to what you could do online via a console or in any other way. But you can, as I mentioned, for the use case of ingesting trillions of log lines, billions of log lines, you can actually start from whatever you want, from scratch, from the smallest thing you can start, and you can add some packages from AWS and do the same thing. So first, reminder, good practice, we're copying requirements first, so we install them and don't have to rebuild when the code changes. We're installing them, and then we're copying our application code. Basic practice, but I like to remind everyone that. And then we're saying that, our entry point, pretty much, our handler is in Lambda under Lambda floor function.handler. With basic compose, just for local testing, we're just going to start with this LLM Lambda image. I'm calling image explicitly, so it has a nice name. We're going to build a local directory, and we're going to map a port. So this basic provided by AWS image is hosted on 8080, but everything wants to run on 8080, so I mapped it to 9000. And when we run Docker Compose app, our function will be invocated under this URL. Why this weird URL? Because that's how AWS specified their API. They did it in 2015. So basically, to invocate your Lambda, you need to call this, and I'm passing empty object as a parameter, as a body, just to demonstrate that. Okay, so that was basic Lambda. You can already use this if you want to deploy Docker files to Docker images to Lambda. So let's now try to run an LLM there. And the most common way you can use right now to run on CPU efficiently is using Llama CPP. It's basically an C++ implementation of common LLM architecture inference. And it uses all sorts of acceleration. So if you use any local language model, app, or package like Ollama or whatever else, this is using Llama CPP under the hood. Very well maintained project, really cool one. And we're going to use a Python wrapper of this one. Then we're going to do another common Docker thing. We're going to use a build stage so that we can have a pretty thin image. You can optimize it further. And then we're going to download the model from Huggingface, as I mentioned, GitHub for language models or for AI models. So what we're going to start is with the builder stage, and we're going to start with regular Python, then do some updates, and we need to install compiler in this one, because we need to compile Llama C++ in the way we want. And then we're going to add requirements. And then as for the flags, you can find them in Llama CPP README pretty much. But what we're adding is adding BLAS. BLAS is a multi-processing, multi-threading library. So we're using OpenBLAS for this. If you studied at university, you probably knew those flags in make files. We don't use it in these days that often, but we're using BLAS because we want multi-threaded, multi-processed runtime. I actually don't know how the work is split, but it works nicely, distributes it, whether that's processes or threads. And with this backend, with this library, we're compiling Llama CPP. And once we have that, we're coming back to our AWS image, AWS base image. Really, I downloaded the model here with Huggingface CLI because it's not that big. The Huggingface CLI, I didn't remove it, but that's what you could do. So, and we're installing a model. The model we're using is Phi2. It's one of the Microsoft models, the small ones. They have a really good performance. You can also use the third version of this one. It has also vision capabilities. When I originally prepared it, I started with Phi2. And we're using a quantized version. So if that's for language models, we are using not full float precision, 16 bits, 32 bits, or 8. We're using actually 4 because that's enough in this case, and that makes the model smaller. You can use other quants as well, smaller, bigger. It works quite well. The next thing we do is we are copying from our builder stage. We are copying our packages, our compiled Llama CPP, and then basically compiling the function code, and then again saying that we want to run our handler function. So now let's review the handler function so we can actually run the LLM. So that's going to be quite straightforward thanks to the Llama CPP wrapper. So basically we're instantiating the model, we're loading it to memory, and we're specifying that we want to run it in 6 threads. Because what I'm going to do is I'm going to configure Lambda to use 6 virtual CPU cores. And as for the context length and underscore context, we are using 2048 tokens because that is the context length that the model provides. So tokens, roughly words in English, or half of the word in English. So we have our handler. The signature is the same, and then we're going to we're doing our runtime. This time the if statements at the beginning is just because locally when I just invoke it with URL without specifying encoding, it just passes my body not encoded, and when you deploy it to Lambda, by default it encodes the body. So I'm doing this distinction so it works both for local testing and when deployed. So we're doing a very simple thing. We're loading the body as a JSON from our post request, and we're taking our prompt to our LLM, and then as an output, we're basically running an LLM, and we're passing a prompt, and in this case, we have a format when we say instruct and output. And when it comes to prompt format, you can find those usually in the model descriptions on Huggingface. And one cool thing we did at the top, as you can see, loading model to memory is done outside of the event handler, outside of the Lambda handler. So when you start a Lambda, it loads once. And once the Lambda is warm, once you reuse it, rerun it, the model is already in memory, and it's a significant difference at runtime. Okay, so now if we run it locally, you can build the container and then start it with our Docker Compose. And I'm basically going to run it with a body, generate a good name for a bakery, and we got a name, and also we're getting some stats because I included them in the response. So that's pretty cool. We have model running locally. Now how to deploy it. The flow is pretty simple, so you can do it in whatever technology you want, but basically we need a ECR, Elastic Container Registry, to push an image to, because every time the Lambda will run or will start for the first time, it will download this image from the registry, from the repository, and then start it. So I wrote a script where I check whether it exists and create it if it doesn't. Then for Lambda, we need specific execution role. We need to upload the image once we build it to ECR, and then basically run an update or creation of Lambda function pointing to this particular image. And what I want to get at the end is to get the URL. So I'm going to actually quickly show you how I did that in Bash. That's maybe interesting in some cases. I'll make it even bigger. Okay, so first thing, regular AWS stuff. So we need to specify a region. Then you need to somehow call your container registry. I called it LLM Lambda. I'm going to deploy always with the latest tag. You want some versioning probably. And we're going to call the function LLM Lambda. You need to call an execution role in some way. I called it LLM Lambda role. And in this case, I deployed it on ARM64 because I compiled it locally on ARM processor, but you can specify architecture yourself. With ARM on Lambda right now, it's 20% cheaper, and they claim it's also 20% faster. So you get two benefits. From my tests, it looked like it is about that kind of difference. So that's good. I've added some policy that's in the repo, basically that you need to allow Lambda to download images from ECR because everything is disabled by default. And yeah, I'm going to disable pages from AWS CLI output because I want to parse some stuff. I'm also going to turn on word wrap so we can see everything. Okay, first thing I'm doing, checking if the container registry exists, because I want this script to be running all the time and I want to start different environments. So I ask describe repositories, and if I find a repository with this name, then that's fine. If not, then I create a repository in a given region with my name. Then what I'm doing is checking if the Lambda role exists again, and if not, I'm creating it. Otherwise, I'm saying, okay, it exists. That feels pretty raw, doing it via Bash, but I want to explain the concept. So the next thing you do, you need to log into ECR. You basically maybe often did that yourself locally. You need to get the credentials from AWS CLI and then pass them to Docker login. And then we build our image. I'm enabling Docker build kit, so it does all these optimizations for caching. I think it runs by default right now. And for build platform, I specified ARM64, but usually, say on a Mac, you can compile for both with a VM, but your mileage might vary. So just run it and check if you can. And then we need to tag the Docker image with the right name. So basically, what I'm doing here is I'm getting my AWS account ID, and then I'm pointing to the right URL in the right region of the ECR, and then constructing my repo name and image tag. Once we've got the proper name tagged, then we can push the image, and basically then we're doing Lambda deployment. And for Lambda deployment, we need to create a role or get the role name. Then if the function exists, we're not going to create it. And then some parameters for Lambda functions. This one is interesting. So for this one, I set timeout at the 300 seconds just to be sure. The executions are much smaller. I'm setting the memory size to 10 gigabytes. And the reason for this is Lambda basically assigns compute based on the memory size. So you don't specify CPU cores, you only specify memory. And basically starting from a little bit around 8 gigabytes, you get those 6 CPU cores available. But also if you increase the memory, you get like more of those cores actually available for you. So I went for the top, and later I tested it with smaller amount of memory, smaller amount of cores, and the execution was just much smaller. So in general, when you're optimizing Lambdas, sometimes even if the function requires, say, 50 megabytes of memory or 1 megabyte of memory because it's just doing a small database query, it may turn out that increasing it to gigabytes increases compute, and the function executes much faster, and you end up with lower costs. Good optimization tip. And so then we need to get a proper image URL so we can specify it for our Lambda. And then we're doing our deployment. So basically, I have two cases where I create a Lambda and update the Lambda. So that's just regular stuff. We specify the name and all the parameters we've specified before. And also the permission for the Lambda to be invoked via URL, because I want to deploy it via Lambda URL, not via API gateway, just for these test purposes. The updates look similar. You just point it to the image again, and the update is pretty simple. And then we get a URL so we can test it. So that's our deployment story. Let's now see results: cost, performance, and others. So I was able to run the same thing on the Lambda. I got similar results. That's a good point. So what was the performance evaluation? Let's start with what we have. So we have 6 cores, 10 gigabytes of RAM, 5 minutes timeout. With cold start, executing this prompt took, on average, with few runs, 17 seconds, and with warm runs, 9 seconds. So loading this model is around 2.1 gigabyte plus the image size. So let's say we're probably at 2.3. Loading 2.3 gigabytes to Lambda, Docker image to Lambda took 8 seconds. Not bad. Then for cost analysis, we have $1.2 per 1,000 runs after free tier, because the free tier is like 4,000 free runs. Okay, so what is the speed and comparable speed? Original GPT-4 ran at 10 tokens per second. It felt pretty slow. GPT-4 Turbo runs at 48. GPT-3 Turbo, or right now probably 4.0 Mini, runs even about 50 to 100. We are getting 9.2. So that's usable. It was enough to put it in ChatGPT, GPT-4, but that's not very fast because we're getting 10 tokens per second. In English, probably like 7-8 words. In Polish, probably more like 5. So what was the cost? You can run this using free tier for 4,434 times. Really nice number. But then it's $1.2 per 1,000 runs. A much better model, 3.5 turbo, would cost 0.2. So that's 6 times more expensive. So unless you're looking for benefits I've mentioned at the beginning, it's not cost effective. And I tried different things to optimize it. So for example, reduced memory, because less memory, you basically pay on Lambda for memory, how much memory you're using for given length of time. So for this is because we got less CPU, the execution was longer and took 26 to 40 seconds. And we got 3.15 tokens per second, so much slower, and it increased our cost, even though we were using cheaper infrastructure. And this experiment confirms that you, even though, because why 3,500 megabytes? Because it was the minimum to fit the model. So the whole model fits in 3.5 or 3,500 megabytes. So this could be enough, but the CPU constraint makes all of this longer. So, you know, if I were you and what I did next to actually take something from this, you can use different models. And as you can see, we used only 3,500 megabytes of memory. You can fit a bigger model. We've got more efficient architectures right now with flash attention and other stuff, and you can run different models. There's also right now a vision model you can run that's very interesting, and everything fine-tuned. As a good sign that why fine-tuned models work, right now, say Apple released Apple Intelligence. It's going to run on phones and laptops. And what they do is basically they have a small language model that's like 2 to 3 gigabytes, and they have fine-tuned LoRa adapters on top of them that do different tasks. So they have image generation in there, they have email summarization, they have notification summarization, and basically what they do, in memory, they swap adapters for different use cases. That's pretty smart, and they decided that few gigabyte model is actually usable for production for on-device use. So if they were able to get the performance that's safe for deployment, even though the results can be sometimes funny, there's something for us to use as well. Yeah, I would also go play around with proper deployment scripts and doing, you know, GitHub actions for deployment, trying different serverless platforms because there's more. Serverless GPU, I don't believe there's a good offering anywhere right now. If there is, then cool. You can easily make this API OpenAI compatible, so you can use it with all the packages. Llama CPP just exposes this API, so a few tweaks to the script, and you should have it. And yeah, subscribe to my newsletter and go there. Shameless plug. All right, that's an old feedback QR, so don't go there. Yeah, that's not it. But yeah, if you like the talk or not, please rate it in the app because the feedback is very valuable and I'm trying to improve there. And as you can see, I'm not selling a book or anything, so this is purely for knowledge exchange. And yeah, if you've got any questions, then let's do it. Thank you.